Hello. All right, this works. So, welcome to the last talk. I'm going to talk about containerized databases in a machine data environment, or rather, how you get the most out of your database. I'm Claus. I work at a company called Crate.io. I've been there for roughly 2 years now, and yeah, the company existed since 3 years, so it's just almost basically 2/3 of its lifetime. We are about 25 people based in Berlin, Dornbirn in Austria, and basically at the Swiss border, and San Francisco, whereas it was founded in Dornbirn, so it's actually a European startup. And yeah, I do a lot of stuff there, starting from developer relations over to some field engineering, whatever that might say, and but I mostly do support, so basically I'm hang out in the Slack channel all day answering people's questions. So we have heard a lot about Go, and I'm going to add Rust to the whole thing. So I am very passionate about Rust in my free time, basically. I also like Raspberry Pi, so I brought the Raspberry Pi Zero with me that has a sensor attached to it that I'm going to use later on to generate some interesting things, hopefully. So you can, if you have any questions about the whole talk and things like that, I have always included here my Twitter handle. You can ask me on Twitter now, or I don't know, in 2 months about the things I've been talking about, and I will respond there. All right, so first of all, I use the term machine data. Machine data is something basically, that's any data that is produced by machines instead of humans, and it's predicted to be basically like the next big data thing, and it's like how big, and the predictions say something like 40 zettabytes by 2020, which is the growth rate is also basically 5 times in the last 5 years, or between 2015 and 2020. It's basically 5 times what it was between 2010 and 2015. But and 1 zettabyte, by the way, is 10 to the power of 21 bytes, so a pretty large number. Yeah, machine data, other than being big, has other characteristics too. So usually you have a high insert rate, so you read a sensor a couple of times a second usually. You have a high data diversity, so it ranges from cameras you attach to somewhere to some temperature sensors that simply output a double value. And you want to have some query performance that spans not only the whole history, but also real-time performance. So you want to have, you want to know about the sensor data right now. And if your house is burning down, you want to know not in 5 hours when the job has finished processing all that data, but instead, or in addition to that, rather, it's also important to know basically when something is warming up and maybe breaking down in the future. So these 2 requirements are also basically also made harder by the exponential growth. If you have, for example, just reducing or increasing the reading frequency from 100 milliseconds to once every 50 milliseconds on a sensor, will just double the data rate immediately. So machine data is generated by a lot of things, including the Internet of Things. So literally anything from a toaster to a fridge, or egg trays, if you want. But also wearables and all kinds of gadgets like Amazon Echo and things like that. And ultimately also logging and monitoring data, as I said, basically anything that's not human. And where it's particularly interesting, though, is in production lines in the case of industrial applications, where you can see basically someone throwing a bunch of sensors at their production line and want to do something or replace humans just looking at things, but instead have one person sitting somewhere and look at a bunch of dashboards and monitors to find out what's happening. And of course, vehicles, if you think of self-driving cars, these are basically the most important or largest data producers in the future. So, and speaking of cars, we have seen a few users like ClickDrive who do car monitoring, who do predictive maintenance on top of that. So they have like 2,000 data points a second per car, and do fleet tracking, which is very popular. Something very similar is Room Monitor that does basically smart apartments for your hotel rooms, basically predictive maintenance in the sense that you can go into the room and tell people to be quiet before the neighbors call, essentially. And yeah, the last but not least is security is also always a very big thing. You have a cloud access security broker that monitors your logins and can figure out basically unsupervised learning, what's the base rate and when something weird is happening, like intrusion detection. So all of that is machine data, and it provides a huge amount of data, and that huge amount of data is usually solved by one common architecture pattern that has been dissolved or has been basically popular in the last few years, and we have heard it a couple of times today. Microservices, of course. You have containers. They let you focus on the specific thing, and they provide the building blocks of doing something with basically the compound of all the containers are your service that you provide. And essentially, by scaling up or horizontally scaling, it's the important part of why you use containers. However, that's usually hard with more stateful containers, and that's what we're going to look at in the OpenStack example. So that's not literally OpenStack, but it's more something very open to use. So as an example, we've seen that with the companies we've been working with. A lot of the times that there's a common architectural pattern they follow, which is you have basically one sensor, you have a consumer of this, so basically the sensor produces some data. It's not only one, it's usually like hundreds or thousands even. One consumer of that sensor data that does something with it, but most importantly it stores it somewhere usually, and some visualizer which is usually a dashboard of some kind for someone. So going forward with this pattern, essentially, we have seen that we have this common pattern, hence the load balancer thing is very important here. So you have the load balancer who does reverse proxying between those basically containers that are deployed on physical or virtual machines here. So basically one stack is one virtual or physical machine. And it routes between those things, basically between those machines as soon as the sensor data comes in from the top. And this is a user looking at the stuff the visualizer draws here. So in this case, we have 3 instances in order to achieve high availability. And this is, this is basically the one part of the backend here. However, there's an important part missing, and this is the data storage. And data storage is a tricky bit, is usually the tricky part. So here in the bottom, we have something called usually Lambda architecture, which consists of basically one slower database in that sense, one thing, something that is a faster layer on top of that, and something to synchronize them in order to not have to insert into both at the same time from your consumer backend here. So, in addition to that, you have sometimes like a monitoring stack and an analytics stack that also has somehow access to the data. But this would be, probably another one of these nice charts to draw here. So, but there's a couple of problems. In this case, you see that there's gray lines connecting every container essentially with the message queue here. The message queue is, what we could call here a single point of failure. Because in order to just scale out and add, for example, more of these stacks here, this would work just fine for as long as the message queue can handle it. But as soon as it's overloaded, it might start rejecting things, and then you have to scale out the message queue, which is usually a bit tricky on its own. And especially these are just message queues and not database, so they are also prone to lose records. And you have also here a bottleneck, as it's already has slight funnel shape here, which basically means that the network can also be saturated at some point. So not only the message queues maybe even scalable, but usually what you have when people run into a problem, when there's a lot of data coming in, is the SQL database. So the SQL database is usually horizontal scalability is always tricky and very hard to maintain, and also it's not feasible in a way that's easy. It's not easy, and it's also not native in a container environment to use essentially. NoSQL databases, on the other hand, work usually quite well with scaling, but they require, as soon as you change it, they usually require a new backend, since the visualizer has to touch both of the databases in order to fetch the data. So we have come up with a different solution here. We have basically added, we have thought, why not replace the database with another database? And there are many of those, and you can choose each one of them. And we have chosen to create our own flavor, and this is CrateDB. And it's a distributed SQL database. So we want to combine the best out of both worlds here. It's open source on GitHub and on a Docker Hub, of course. And we've had our release in December, and a few fans out of the Docker community reacted. And CrateDB itself is basically a shared nothing database. It has partitioning and auto sharding built in. It uses replication on the software side. Has very sane defaults, so that that you can almost use no configuration at all in order to start a cluster, which makes it basically, otherwise you would replace your operations management with configuration management, and that's also not really good. And it supports a multi-model structure, multi-model data in order to basically, store structured and unstructured data and offer it via SQL to the outside world. So in this case, you have basically, you want to do some the fundamentals of Crate allow basically, or understanding the fundamentals of Crate allow to know where the data is really stored. In this case, it's really always stored on disk. So it gives basically it stores anything on disk and uses in-memory caching in order to achieve speed. So there's nothing stored or held in memory in particular unless it's queried. So which means you always know where the data is located. And the data is located always basically in shards, and these shards are shuffled around the cluster automatically. And this is how it achieves basically concurrent operations, by always working where the shards are. So basically the queries are pushed down to the actual nodes. So in this case, looking from a bird's eye perspective on a Crate cluster would mean that you have a client connecting to either one of the nodes. So basically these are also black lines, just like here, connecting the client with the nodes. And they can connect with either Postgres wire or HTTP, go through. Every node can do the parsing, can do the planning, and can do the execution, and basically involves all nodes into the processing, which means that it's a cluster, and the clustering is formed, or basically for the clustering, Elasticsearch Sen discovery is used for that. and we use Lucene as basically the storage engine beneath all that. So what we are usually doing with our clients is then propose a better setup for that, and this is of course a vastly simplified version of that. What we provide them with, it's a horizontally scalable stack, in that we add just the database basically to every node here, and we provide only connectivity between the nodes just for the database. And this, basically by doing so, you can always access the data you want to have or you want to store on localhost. Essentially, you don't need to expose the database to the outside world, as we have heard. There were some incidents a couple of weeks ago with MongoDB, for example, with exposed ports and automated attacks. That also reduces the tech stack significantly, and enables basically also very live reporting. So by adding a node, you can just look into the production data, how the whole thing works. So yeah, most importantly, it removes also the point of a single point of failure, and by just adding another of those stacks in whatever composition, you can just scale out in order to accommodate more traffic, So I have been talking a lot about that, but I can also show you that in a very, very small form, of course. So what I've brought with me is also a Raspberry Pi, Raspberry Pi Zero to be exact, where there's a Docker container, or it runs in a Docker container. It runs a Docker container with a Rust application that features, a driver for this temperature sensor. That is basically a Bosch temperature sensor, BMP 180. It's of course compiled for ARM, currently it's not part of the swarm, unfortunately, but the rest is part of a Docker swarm orchestrated service, and they are running the server part of the whole thing, which is a RESTful API that does some authentication and receives a JSON and saves it into the database. And we will use also Grafana in a bit less colorful way maybe than we have seen before, but it will output whatever the sensor reads. So I plugged it in the beginning of the talk, so it should have gathered some data already now. And yeah, let's look at it. So before all that, so this is basically how I deployed the whole stack using a Docker Compose version 3 file. So it utilizes a swarm basically, or it utilizes swarm mode. It creates 3 services. In this case, CrateDB is the first one. It uses our Docker image. You should, of course, use, in a real-world environment, you should maybe use version nailing. As I said, the simple configuration, you can just add the heap size and use maybe half the limit of the Docker container, that basically to accommodate some space for caching there. And Crate uses essentially 3 very important things here are to configure here, which is then the expected node, so that the cluster knows how big it should be. Then the recover after nodes option, that it knows when how many nodes it should expect in order to start recovering. So at least 2, which is a quorum, and also basically the minimum master nodes, which is also when should it start electing a leader. Then we disable multicast because it doesn't work on a software-defined network, and instead use unicast. Then we bind to ETH0 in order to don't leave that up to random, and we call the cluster New York City because that's where I came up with the talk. yeah, we attach two networks, one for client, one for Crate to talk to, and here we can, and here we map the volume. So this is basically where all the data is located. And this should be in a better production environment. This should be, of course, something like an attached EBS volume or something, something where you know and you care about much more than the data, basically where the data should be located. In addition to backups, of course. And the deployment mode here is global, so it always deploys exactly one container per instance, which is, yeah, exactly what we want. Also, very IOPS intensive applications tend to not work well in the same node, usually. And as a placement constraint, we use here the manager node role, basically, because this is, in this case, it's just a lazy variation of not using labels. Then we deploy Grafana. The same thing, expose port 3000 and install the Crate data source plugin in order to have something available there. And we have Eden Server, which is the component I created basically for myself to monitor this sensor, to basically consume the sensor data. And if the ARM thing, basically the ARM thing would be part of the swarm, we could also add the client application here and just deploy that as well. And then we add, of course, the networks. Of course, I have already done that. So what we see here is essentially that. So, if it would respond, yeah. So we see that there's 3 hosts in there. We have basically, they should all be managers, but we only have 1 leader. We have deployed that Docker stack. We have these services up and running. So there's, since this is global mode, 3 replicas. We have, but we have Grafana in a replicated way, since this is only, it would only make sense to have it once now. And yeah, let's look at the actual thing here. So this is the Crate cluster. This is Crate's admin UI. We see that there's 3 nodes here. They're all nodes that run on Packet, since it was also mentioned earlier. These are Packet type 0 machines. So they have 4 cores and a bit of memory there. They are very bored, as we can see. We can also see that here in the overview. And each of them has, so there are a couple of tables already in there. And I've imported some data that in order to show that this is already also capable of handling a bit of data in there. But I think it's, it should be inserting. So this number should change every couple of seconds. And this is the data model. So Crate supports, basically in this case, it supports object types that are dynamically expandable. So this sensor can handle basically temperature data and air pressure. And this, in order to accommodate that, for if I wanted to add something like a luminosity sensor maybe, then this would be just another field in that object, and I could filter by it, I could query by it, and slice and dice through it. And the same goes for the meta, basically object that could handle more Raspberry Pis or Odroid or Banana Pis or whatever else there is. So we can basically filter by that as well. And the timestamp and the month is generated from the timestamp itself there. And I think it should have changed a couple of times already, so we could see something. So if we look at Grafana now, we see that this is basically the real temperature data. So this is actually a Raspberry Pi that is in my living room in Berlin. So we see that there's 19 degrees currently. And we see that that there's been things going on, like windows have been opened, doors have been opened, and there's draft, and it changes the temperature. It doesn't change, it doesn't vary greatly, but it does. These spikes are usually like windows being opened and closed. We can just change here to the data we have here. So that's, of course, a bit less. So 24 hours is maybe a big window here. So in the last 50 minutes, by the way, these are all live queries that are always executed every time there's this small thing appearing up here. So every time we change something, these are live queries in the Crate database. And the query is basically the 10 million records. Find something. Oh, it's the wrong data source. So yeah, that's basically it. We see that this is running, and I said, yeah, this is highly available. So I've touched it a couple of times, so it has actually gone up and down. So we see that this is a 3-degree change. But as I said, this is highly available. We could just stop one instance and see what it does. So as you can see now, the cluster has only 2 nodes. It has basically one node has died a tragic death, and this now is under-replicated. It tells you that this is a warning. So we have accounted for that. We have added one replica. So it's fine. It starts re-replicating, and it starts moving data from one side to the other side again, or to the other 2 nodes again, in order to re-establish the initial state. And the cluster itself also saw that something is wrong here, and you actually should have 3 nodes, but you only have 2. So it's kind of warning you that this is something you should take care of. But at the same time, the things just have, it didn't really bother the sensor insert, so that the thing is still inserting. This is still working well, and it's basically querying every 5 seconds the database. So there's no disruption there. Yeah, and that concludes it also. So what I've shown you is basically that we can do some ad hoc analysis, basically with SQL queries. So Grafana is a very elaborate way in this case to create a nice SQL query. We can also run some other things in there. So I have a few queries if you're interested afterwards. This way it integrates well. Crate integrates well with the whole, with existing applications and other applications that only speak SQL quite easily. So we could also do that probably with Postgres instead of Crate, and it just would work in a very similar way. But it wouldn't be horizontally scalable, which is what Crate is basically good at, to be more container native and therefore highly available and more prepared data store for machine data. So and that's it. So thank you for your attention. We have I have made all that stuff in my GitHub repository available, but it's Crate's GitHub repository and the Docker Hub and our website, and you can follow us on Twitter and ask questions now or later. So thank you.